Hi class, so today we'll be talking about chapter 8 and this is all about waves. So there are three types of waves that you can find in the atmosphere and in the ocean. The first is it should be familiar to you because these are just ocean waves. So these waves are created between the atmosphere and the surface of the ocean. They are also known as surface waves. The second type of waves are atmospheric waves. These are created between different air masses in the atmosphere. The troposphere is the part of the atmosphere in which we as humans live in, and above the troposphere is the stratosphere. So in between those two air masses lies a transition area known as the tropopause. It is here where you can see these atmospheric waves being generated. An example of these waves is shown in the image on the left on the slide. You can see that the image on the left shows clouds that are rippled, much like what you would see in the ocean as a wave comes by. And lastly, there are waves that are created between water masses in the ocean, and these are known as internal waves. Looking at the image to your right, you can see that internal waves occur at depth between two water masses. You can see this when looking out of the airplane window down at the ocean surface. There will be what looks like two sets of waves, but one is going 90 degrees to the right of the surface waves. Those are the internal waves. Now there are three types of wave movements that these waves can exhibit. The first is longitudinal waves. This motion causes the particles to push and pull in a horizontal direction. So in the image below, you can see that the spring is an example of longitudinal wave movement. These waves are also known as P waves. The next are transverse waves. These waves have an up and down motion and are also known as S waves. So one example of P and S waves are when you look at earthquakes. Earthquakes exhibit both P and S waves. So that low rumbling noise that you hear before the shaking starts, those are P waves. Those are causing the rocks and material in the crust to move side to side. Then, once the shaking starts to happen, that's where S waves come into play, and they start moving all of the rocks and soil and particles in the crust up and down. The P waves are faster than S waves, so that's what you'll hear first before the shaking starts. S waves will follow shortly after that, and that's when it is associated with the shaking of earthquakes. One important thing to note here is that both P and S waves are still separate and are not one wave when it is associated with an earthquake. So you have these two waves traveling together, but they are separate. Whereas if we look at our third type of wave, orbital waves, those waves is a combination of both longitudinal and transverse waves. So these orbital waves are what we see in the ocean. And these types of waves, just like the name suggests, will have a forward moving component as well as an up and down component. So on the next slide, you'll see what I mean. In this animation here, you should see how an ocean wave propagates or moves through the ocean. If you focus on the red dot, you can see that the movement of the water molecules are different at depths. You can see that the molecules at the surface create a much larger circle than the molecules at depth. And this is because in order for the wave to travel at the same speed, all the molecules have to be traveling at proportionally the same motion. So because the molecules at the surface are moving faster, they have to move in a larger circle than the ones at the bottom. Also too, you can see as you're looking at the red dot making an orbital circle. It has a forward moving progression as well as an up and down movement to it. The wave structure, the basic wave structure, includes the top of the wave, which is also known as the crest, and the bottom of the wave, which is known as the trough. There is the wavelength, which is the distance between two crests, and then there's a wave height, which is the distance between the crest and the trough. So for those of you who like surfing, you would really care about the wave height. Other things to consider is the wave steepness, which is the difference between the wave height and the wavelength. This difference needs to be greater than 1/7 in order for the wave to break. So when you see waves breaking on the beach, you know that that wave crashing on the beach has reached the magical 1/7 steepness point, and it will be crashing. There also is a wave period in which you are looking at a fixed point, and you look to see how long it takes for one wavelength to pass by this fixed point. This can help you with the wave frequency. This wave frequency is how many crests pass by a fixed point in a given time. So the faster the waves are traveling, the shorter your wave period, and the larger your frequency of waves are. What we see of the wave at the beach is just on the surface. There is a bottom to the wave that can be calculated as half the wavelength. This bottom is the deepest part of the wave and can be affected by topography on the ocean floor. So let's look at 3 types of waves out in the ocean, and the first one we'll talk about are deep waves. So deep water waves occur out in the open ocean, and they have depths, basically bottoms of the waves, that are greater than half the wavelength. That means that the bottom of the waves do not touch the ocean floor. Granted, now out in the open ocean, your ocean floor could be as deep as 4 kilometers. So most ocean waves that are created do not have bottoms that go that far down. They typically have a rounded shape to the wave at the surface, and their wave speed is determined by the wavelength divided by the period. So that means the longer your wavelength, the faster your wave will be traveling at the surface of the ocean. These types of waves are generally known as swells. Now, shallow water waves are your next type of waves. These ones are the ones that you see breaking on the shore, and they have depths of 1/20th of their wavelength. So that means the bottom of the wave is definitely touching, or what we call feeling, the bottom of the ocean floor. These are also known as breaker waves and have a very distinctive curl and shape to the wave. And lastly, you have transitional waves, which are found in between deep and shallow water waves. These types of waves show characteristics that are similar to both deep and shallow waves. So their wavelength could be anywhere between 2 and 20 times the water depth. So that means at a certain point, maybe these waves, the bottom of these waves will not feel the bottom of the ocean. But as the slope starts to increase, it will definitely feel the bottom, and the wave on the top will go from a rounded structured shape to more of a peaking shape. So these are also known as peaking waves. And when it gets to the point where it becomes a shallow water wave, then it will transition into a breaking wave. How do we get waves? How are they generated? Generally speaking, they are generated out in the open ocean, and they need an energy source. That energy source is wind it will always be wind for surface waves. This wind will then blow on the surface of the ocean, and it will transfer some of its energy to the ocean. When it transfers that energy, your waves will start off as capillary waves, and these are little more than bumps on the ocean surface. Now, if that wave continues to blow over the ocean surface, it will continue to transfer its energy, and it will turn into ripples. Then, if the wind continues to blow, it will turn into chop, which will then turn into wind waves, which will then turn into fully developed seas, and finally you'll get swells. The area in which the wind imparts energy to the water is known as the fetch. Waves typically, from capillary waves to fully developed seas, are in the fetch area and are still receiving energy from the wind. Once the waves become swells, they leave the fetch area but have enough energy to continue propagating through the ocean in the direction in which they were generated. Factors affecting wave generation are these three shown above: wind speed, duration, and fetch. So the wind speed needs to be strong enough in order to transfer energy to the ocean. Now, if you recall from chapter 6, wind can only transfer about 2% of its energy to the water. So if the wind speed is not strong enough, then it won't create swells. Likewise, if the winds do not last very long, then swells will not be created. So you need to have a long-lasting wind, you need to have a strong enough wind, and you need to have a large enough fetch. If your fetch is not large enough, it cannot create very many waves. So definitely the larger your fetch is, the more waves you can create. The stronger your wind is, the more waves you can create. And as long as you have a sustained wind source, you can create waves. Now, when you're creating waves in the fetch area, you're not just creating one wave at a time. You're creating multiple waves all at once. And when you do that, these waves sometimes will interact with each other. There are three types of interactions. The first is constructive interference. This is when a crest of one wave meets the crest of another. And when that happens, it has an additive effect, and the resulting wave is much larger than the first two original waves. So you get a much larger wave. Then you can have destructive interference, where the crest of one wave meets the trough of another wave. When this happens, the resulting wave is canceled, and you essentially destroy the wave. So you get no wave whatsoever. This is what happens when you wear noise-canceling headphones. The headphone sends out an opposing sound wave that cancels the noises that are coming in from the outside. And lastly, you have mixed interference, which is when you have multiple waves combining at different phases, and this will give you a varied resulting wave. Now, rogue waves are something special and aren't always created, but rogue waves are very, very large waves, and they are created by constructive interference. Now, generally speaking, they don't know exactly the mechanism as to how these waves are created, but they think multiple waves come together and combine by constructive interference to create a giant wave. These waves can sometimes be as high as 200 feet tall. So these are very dangerous, and a lot of cruise liners and large ships have actually been sunk by these rogue waves. And typically they only occur in certain areas around the world. So just be careful. Next, let's talk a little bit about breaking waves. So breaking waves are those shallow water waves that we were talking about in the previous slide. And these are the waves that come in contact with shore. So the bottom of the wave starts to feel the ocean floor, and it causes the water molecules at the bottom of the wave to start to slow down in comparison to the rest of the wave. So it's just the molecules at the bottom of the wave that are slowing down. Everything else is continuing to move forward at the same speed. So you have this leaning over effect that you can see in the image there. And the molecules at the top of the wave start to get pushed up and start to peak. And as that wave continues up the slope, the beach slope, the molecules at the bottom of the wave will continue to slow down, causing more water to be pushed up. And eventually, once it exceeds its wave steepness, the wave will then crash into shore and turn into a breaking wave. There are 3 types of breaking waves that you can see on shore, and this is dependent upon the beach slope. The first are surging type of breaking waves, and this type of wave occurs when the beach slope is very flat and very gentle, and you can see it just kind of pushes along. There's really no curl to the wave. The second type of wave is spilling breaking waves, and those are created when you have a medium sloped beach. So there is some slope to the beach, but not as much as the next type, which is plunging. Plunging waves have a very steep slope for their beach, and so it creates a sudden uplift of the water, and that creates that nice curling wave that most surfers like to surf on. Next, we have wave refraction. So here, the wave comes in contact with the shore, and when it comes in contact with the shore, the energy from the wave doesn't just dissipate. It starts to form according to the topography of the shoreline. So when a wave hits that headland that's in the image in the slide, you can see that it'll hit the top of the headland, and the rest of the wave will curve around the headland and start to lose energy. So when the wave hits the quiet beaches that are on either side of the headland, it's significantly reduced in energy, and it doesn't cause any erosion on the beach. All of the erosion occurs on the headland, on the very top of the headland. So that's wave refraction, where it bends around topography. The next is wave reflection. So if you look at the image on the right, this is essentially when a wave hits an object and bounces off of the object and is redirected in a different direction. So in this particular case, you can see that the waves are hitting that break wall in that harbor, and they are being reflected in an opposing direction. In the image on the left, you can see that the waves are hitting that island. They are refracting around the island and then being reflected in a different direction. Then you can have special waves, which are standing waves, that don't really propagate forward or move forward like regular ocean waves do. These particular waves look like they're standing still, and generally speaking, these waves are created in an area that allows the topography to keep the wave there, and then you have high winds keeping them in place. So this allows surfers to practice or surf and not really have to wait for a wave, because the wave is always going to be there. This type of wave only occurs in certain places around the world under special circumstances. And then we have tsunamis. Tsunamis are waves, but they're not like the ocean surface waves. that we've been talking about because they are not generated by wind. They are generated by seismic activity. Now, this seismic activity needs to be large enough to displace a huge amount of water in order for a tsunami to occur. So whenever we have earthquakes in the Pacific, it doesn't always generate a tsunami because it doesn't displace enough water to create one. The tsunami is a special type of wave. In Japanese, it's known as a harbor wave, or the word tsunami is Japanese for harbor wave. And this type of wave has a very, very long wavelength compared to the ocean waves that we've been talking about. So, because it has a really, really long wavelength, that also means that the depth or the bottom of the wave is very deep. So when this type of wave comes in contact with the shoreline, there is a sudden uplift of water, and then it causes a sudden rush onto land of that water, causing severe damage to coastal regions. The image on the top right is from the 2011 Japan tsunami that hit up near Sendai, the Fukushima power plant. And you can see just how much damage this particular tsunami is causing. You can see it is just picking up whole cars and just moving it. So these types of waves are very dangerous. And how do we find out that we have a tsunami? Well, around the Pacific in particular, but there's also some buoys in the Indian Ocean now after their tsunami. But we have this alert system known as the DART buoy system, and this particular buoy system is made up of two parts. There is a surface buoy that communicates with satellites on the base station, and it collects data from the bottom pressure sensor, and the bottom pressure sensor will measure any differences in pressure near the bottom of the ocean. So if a tsunami were to pass by one of these buoys, the bottom pressure sensor would notice in the pressure, and it would send the signal to the surface buoy, which then would send the signal to the base station, letting them know that a potential tsunami was created and is traveling through the ocean. And then scientists at the base station would need to analyze the data that is being collected and actually confirm if a tsunami was generated from an earthquake activity or not. So when the buoy sends a signal to the base station initially saying, hey, something's different with ocean pressure, that's when a tsunami watch is issued. And only when scientists have confirmed what the data from the buoys are will it turn into a tsunami warning if a tsunami was generated by the earthquake. So there is some lag time between the watch and the warning, but generally speaking, they will tend to throw out a tsunami watch shortly after earthquake has occurred, just to keep people on alert. But a lot of times that tsunami watch will be eliminated once they analyze the data from those buoys. So this is one way of alerting people of a possible tsunami threat. These waves do travel very fast through the ocean, so it is important to have ample warning to get people away from coastal regions, just in case an actual tsunami does come by. We've had some pretty devastating ones here in Hawaii. 1946 and 1960 were the last two tsunamis that made or had significant coastal damages.